Hello students, welcome back. Before going over to section 4, let's have a brief recap. First, in section 1, we went through the definition of the function along with its main idea. Each element in the domain is assigned to one and only one element in the range. And of course, there were some preparations and backgrounds and things like those as well. And then we went through the most essential and the most important and also the most difficult aspects of the graphs of functions. And then after that, things got progressively easier and relatively less important. We went through in section 3, increasing and decreasing nature. And then now in section 4, we're going to study the symmetry. Here are 3 basic symmetries, which we went through already in lesson 3b. Symmetry about the y-axis, change the character, substitute x by negative x and see if the result remains the same. Symmetry about the x-axis, again the same deal, change the character, substitute y by negative y, and see if the expression remains the same. Symmetry about the origin, replace both characters, x by negative x and y by negative y, and then see if the expression remains still the same. This is a general case which includes the implicit relation, and this one is the explicit form, y equals to f of x form, the kind of situation that we emphasize here in lesson 5. So what do you mean by this? Replace x by negative x, and then left-hand side remains the same, y. So the conclusion is f of negative x is equal to f of x. If this happens, we call that function an even function, and the graph of an even function has symmetry with respect to the y-axis. Here's an example. We have y equal to x squared, so replace x by negative x, then negative x squared is the same as x squared. So we have an even function, and as you can see, we have the symmetry about the y-axis. And a little bit more general case, like circle. In this case, we have symmetry not just in y-axis, but in x-axis as well. And the same example, we went through this before in lesson 3b, so you must remember, replace x by negative x, or replace y by negative y, or even both of them. They all remain the same because we have even power there. Same goes to this. We have all 3 symmetries there. Okay, remember this term, even function. Another thing that you have to remember is the odd function, and that's for this. Replacing x by negative x and also y by negative y, and see if the expression remains still the same. We went through this already in lesson 3b, and that was for a little bit more general case, implicit equation case. But for explicit case, y equals to f of x case, we still have the same thing, but it can be simplified a little bit further. Substitute x by negative x, so we get this. And substitute y by negative y, so we get that. And then simplify a little bit. Flip the sign to the other side, then you're going to get y equals to negative of f of negative x, right? And then compare this with that, and we get the conclusion. F of negative x is equal to negative of f of x. If that happens, we have to have the symmetry about the origin, and we say the function is an odd function. Here's an example. Wait a minute, this looks like an implicit equation, but that's okay because I can always solve for y, and y is equal to 1 over x. Now this is explicit form, y equals to f of x form. And this one is an odd function because it can be written as x to the negative first power, and this is an odd number. It's an odd integer. Also, look at the graph. Symmetry about the y-axis, symmetry about the origin. So that's the odd function, symmetry about the origin, and this is the even function, symmetry about the y-axis. As for the middle case, symmetry about the x-axis, you don't really have to worry about it for graphs of functions. For the general case, We studied these in lesson 3b, but in case of functions, it's not that important because you see, if you replace y by negative y by negative y, and then simplify by flipping this negative sign to the other side, what do you get? Y equals negative f of x, and then compare with original y equals to f of x. So we have to have f of x equal to negative f of x, but that only happens when f of x is constantly 0. So unless we have a zero function, the trivial case, this will never happen. So you don't have to worry about the symmetry about the x-axis. The symmetry about the y-axis, that's important. That's even function. Symmetry about the origin, that's also important. That's the odd function. There's some properties here, and the definitions are there. Let's see, do we have any further explanation? No, not further explanation, just example. And then please note that even function, they all have even powers. 1, that's x to the 0 power, as a matter of fact. X to the 0 power is hidden. And 0 is an even number. And then minus 7, x to the 2nd power, 4th power, 6th power, they all have even powers. And consequently, if I replace x by negative x, they all remain the same because even number, negative 1 to the even power is positive 1. So no change there, therefore we have symmetry about the y-axis. This is an example of an odd function. Now this time, nothing is here, that means power 1 is hidden. So first power, third power, fifth power, seventh power, they're all odd powers. In that case, we have an odd function. We have symmetry about the origin. If I replace x by negative x here, then negative to the odd power. So we have negative of x to that odd power. And that applies to each term there. So we have this relation there. Symmetry about the origin. Some properties, I could prove those, but that's a bit too pure mathematical, so I'm not going to do that. I'm going to leave that to interested students. Even plus even is even, odd plus odd is odd, even plus odd is neither. For multiplication, we have something interesting. Even times even is even, odd times odd is even times odd is odd. And they don't really act like even number times odd number, as a matter of fact. They act more like even number plus even number is even number for those integers, you see. Odd number plus odd number is an even number, and even number plus odd number is an odd number. So all this multiplication here fits the even number, odd number computation in set of integers for addition. Why is this happening? That's because that's related to the powers. You see, the idea is, so if you have x to the p power times x to the q power, then this is same as x to the p plus q power. Oops. I hope everybody's comfortable with that. And even function times even function, for instance, corresponds to even power plus even power. And for example, odd function times even function, for instance, is associated to odd number plus even number in terms of powers. That's how they are related. I could prove them, of course, but that's a bit too mathematical, so I'll stop there. Division works pretty much the same thing. So much for even and odd and the symmetries. As I said before, section 2 is really, really important and also difficult. And section 3, a little bit less important, comparatively speaking, and a little bit easier. And for section 4, again, even easier, and in terms of importance, even less important, comparatively speaking. So you see, progressively things are going down. Now, if you really have to study these materials before the exam or something, make sure you understand section 2 first. Get yourself absolutely comfortable with that, and then if you have time, go back to 3 and 4 like that. That's my advice.